Here we're going to do an example of path integration in the context of a conservative vector field. And this is actually problem 6 from section 9.9 of the textbook, ZIL, the 7th edition. It's also was a midterm exam question for the 2275 midterm exam. It was problem number 2 on that exam. And the problem statement basically says show that this line integral, okay, from this point, 1, 0 to 3, 4, so it's a specific start and end points. We have some function, x dx plus y dy divided by x squared plus y squared. So to show that this integral is independent of path. Furthermore, it then says evaluate this integral 2 ways, using a potential function, and then number 2, using any convenient path that's not through the origin. So when we look at this problem, there's a bunch of things going on here. The first thing is that show that this is independent of path is asking a question of whether we realize the features of a conservative vector field. So if a vector field is conservative, it means 4 things. Number 1, we say it's conservative, that's the first thing. But that means that the curl of f is equal to 0. That means that the path integral of f dot dr between any 2 points is independent of path. And finally, that you can find a potential function for the vector field that you can use and evaluate that potential at the endpoints of the path, and the difference between the potential function at those endpoints will equal the line integral. So those are 4 things, and they're all elements of this problem. So the first thing it says, like, show that this is independent of path, is really a matter of showing f is conservative. And then the fact that f is conservative means that there is a potential function we could use, and we could use any path between the endpoints, and they get the same answer. So there are like 3 parts to this problem. The first part is show it's conservative, or show it's independent of path. So you identify what the vector field here is. Now here it's not written, you have to look into that to see the vector field. The vector field is xi plus yj divided by x squared plus y squared. So this is really f dot dr, right? So we've talked about this a lot in this course, so we can see that now. We have to check if f is conservative. So that means that we'd look at the curl of f and show the curl is 0. That's what this really means. So we set up the curl in general. Okay, I'm setting this curl calculation up like this is a 3-dimensional vector field. That's just how I remember it. It does two of the terms in the curl go to 0 automatically. We'll show that, but you could actually go to this last phase if you knew that. So you set up the determinant form, have the ijk and the partial derivatives, and then the x component, the y component, and the z component of the vector field. So the first is I by 0, and then this thing doesn't depend on z, so the partial with respect to z is 0. So this x component of the curl is 0. We know it's only going to have a k component, but let's just pretend. J, so we have 0, z dependence here, 0, so the 0 y component, and then k has di by dx of this thing minus di by dy of this thing, and those are non-zero. Okay? So I just write that formally here. It's good to just separately calculate the partials. Don't try to stuff it all into one step here. So here I'm just going to say, hey, what's di by dx of y, x squared plus y squared to the minus 1/2? In other words, this first term. Just what is that partial? So y is a constant, so y comes out, and we have minus 1/2 y, x squared plus y squared, all to this minus 1/2 minus 1, so minus 3/2. Then multiply by the partial of the interior part with respect to x, so it's 2x. Simplify, 2 1/2 cancel, minus xy, x squared plus y squared to the minus 3/2. Simple. Now, you could just see, you could do, when you do di by dy of the other term, it's exactly the same as y versus x. So the x is constant, you do the partial, so you get minus xy, x squared plus y squared minus 3/2. The same thing. So, right away, since it's the difference, this is going to be 0. We can write the curl of f is this k, so it is 0. Technically, it's a 0 vector, right? We don't sweat that. It's common just to write the curl of f as 0, even though it should be 0 vector, which means every component of the curl is 0. We know what that means. Okay? So this proves it. This demonstrates that this f is conservative and this integral is independent of path. That's part 1 of the problem. Okay. Part 2 is then, and we choose to do this next, is to find this potential function. So I'm gonna leave this integral here because we'll need it, and we know we're gonna find a potential function and then use any path between the two to solve it. So let's just erase this part here, erase this part. Okay. So, to find a potential function, what we're saying is that f is actually equal to the gradient of some function phi, right? And phi is a function of x and y in this case. If this is a three-dimensional problem, it'd be x, y, z. Okay, but here we're just x and y, so it's a function of x and y. So what does this mean formally? Well, this means that f, the x component of f, which was x squared plus y squared minus 1/2. That's what we were given in the problem. That's this part here, right? The x component of f. We say that x equals the gradient of phi. So this is the is equal to di phi di x, and we're gonna have to solve for phi. It's a differential equation. We also know that y, x squared plus y squared minus 1/2 must be equal to the partial derivative of phi with respect to y. Okay, so we have two coupled partial differential equations. It sounds harder than it is, but that's what we actually have. So what we do is we start with one, we integrate a solution for one, then enforce the second equation, and those two together will define phi. Okay? So we'll say, okay, so we'll start here, we'll start with the one, we'll say that phi equals the antiderivative x squared plus y squared minus 1/2 x. Okay, that's what the first equation means. We're just integrating to find the solution. It's kind of like the easiest of the ODE type examples. Okay, so we'll let this is a substitution. We'll let u equal x squared plus y squared. So du over 2 is dx, right? Du is 2x dx. We have an x dx, so oh, sorry, this should be x dx. Right? Sure, that's why I never do these really fast. Okay, du dx equals 2x. That means x dx equals 1 over 2 du. Okay, so phi equals 1 over 2 derivative u to the minus 1/2 du. So that's 1 over 2 u to the 1/2 divided by 1/2. Make those cancel, and then we can substitute back u as x squared plus y squared. So this thing means that, oh, one thing I should say here, right here, plus g. I'm gonna write that in a minute. So phi of x and y is, and I'll put u back in, so it's the square root, I'll say x squared plus y squared, 1/2, that's what u is, plus some function of y, right? So this is a constant of integration because the integration is only with respect to x. This thing is not just a constant, in general, it's a function of y. So this is what we got so far. We're not done yet because we don't know gy. So how do you find gy? Well, we enforce this equation and solve for gy. So what we're going to require is that the partial, so we'll take the partial, so I'm going to say that the partial of phi with respect to y is di by di y of what I just solved for here, including the gy, right? That equals, let's just execute this. So that equals 1/2 x squared plus y squared to the minus 1/2 times 2y plus g prime y, right? All we know is the derivative is gy, that's its derivative. So that equals, I'm just using this form here, that equals y x squared plus y squared minus 1/2 plus g prime y. Okay? That's what I got. That's this side of the equation. I know that phi, from this whole equation here, I know that phi of x and y looks like this. So now I take its derivative with respect to y and simplify it. And now I set that thing equal to this. Okay? So now I say, well, this whole thing must equal, and you can see what happens, y x squared plus y squared minus 1/2. So this means that g prime y equals 0, which means that g is a constant. Okay. So I know that, finally, phi of x, y simply equals x squared plus y squared, square root, plus some constant k. Okay? Not a function of x or y. Okay, now, why did we calculate that potential? Well, the whole point is this integral now of x dx plus y dy square root x squared plus y squared actually equals phi at 3, 4 minus phi at 1, 0. That's the whole point. That is the difference in the potential at the endpoints. And this is very easy to calculate. It also means, notice that the k cancels off. So once phi is constant, it's gone. It does not mean that this term is not important. There are other cases of potential where you will find some function of y that's significant here, and it will be included in here. It just so happened in this problem, our constant of integration of y turned out to be a true constant of integration, and we take the difference, it doesn't matter. And this is akin, we talk about potential functions, right? You think about gravitational potential. Remember, it didn't matter the absolute height. What's the gravitational potential at 5 meters? It doesn't matter. It's 5 meters with respect to something else. Only differences in gravitational potential mattered. But that's true of potential functions in general. If something is equal to the derivative of it, a constant added to it won't impact the definition of f. So, okay, so what is this? So we take this and you just literally go, okay, x of 3, so that's 9, plus y of 4, so that's 16, minus x is 0, so it's 1 plus 0. So this thing is square root 25 minus 1. So that is 5 minus 1 equals 4. 4 things, right? 4 joules. If f was a force, and we're doing this work integral, then this would have units of joules. We have some coefficient that would tell us that. Okay? This is the answer to this integral. Although there's a bunch of work to find the potential function, once you find it, using it to evaluate this integral is easy. And notice that this is the potential function for this integrand. Regardless of endpoint, we could use that result to find this. Okay, so now we've done the second part of the problem. The last part of the problem said, okay, finally, show that, frankly, you get the same answer, if you integrate this contour integral on any path between 1 and 0, 3 and 4 to 1 and 0, that doesn't go through the origin. That was a statement in the original problem. So let's just take a moment and ask what that was about. What's the origin? Well, the origin is 0, 0. What happens to this vector field at the origin? Well, that's a singularity. You'll call it a pole later on in signals and control theory. Not signals, but control systems. So it's a pole of this thing. So this theorem, the definition of f conserved, doesn't apply there, right? That's one of the exclusion rules. So we can't have a contour go through that point, right? Because that's a point where the theory no longer applies. Okay? We don't see these kinds of things very often in these problems, but this is one. Okay. So let's do this. Let's go back. So I know we're going to get answer 4. Let's go back here and start this integral again using kind of the older way. The ways that we learned first. Now the difference is you can choose your path of integration now. You're not given a path. Okay. So, here's y, here's x. I've got x is 1, y is 0. I've I've got x of 3, y of 4. Okay, those are my 2 points. I'm going to choose a straight line between those points. Okay, well, from there to there, that's going to be my C. Okay, you also could step this way and straight up. You get the same answer, doesn't matter. What is this equation? Okay, well, just in case you forget, right? So the general equation for a line would be y minus y naught, x minus x naught equals m, where this is the slope. And we happen to know the slope in this case is 2, right? The rise over run, so the rise is 4, the run is 2, so this equals 2 here. Okay, and then x naught and y naught are any point on the line. So we're going to say 1, 0. So this means that y minus 0 divided by x minus 1 equals 2. So that means that y equals 2, x minus 1, y equals 2, x minus 2. Then you can check it, right? If x equals, when x equals 1, y equals 0. When x equals 3, y equals 4. That's the equation of the line. I think people have long since forgotten this, right? You just go y minus y naught, x minus x naught, y naught, x naught could be any point on the line. You figure out the slope by 2 different points on the line. So once you have your slope, that's it. And you substitute any value on the line into this equation. It didn't have to be this point. I could put this point in here, I get the same answer. Okay? So that's my equation of the line. Y equals 2x minus 2. Okay? So, let's do this integral. So I'm going to parameterize this integral. Okay, I'm going to parameterize with x. What does that mean? That means we're going to eliminate y in favor of x. X is going to go from 1 to 3, and we're going to replace all the y's with 2x minus 2. That's the idea here, right? So we have our y equals 2x minus 2. That means our dy equals 2 dx, right, in our equations. And we're going to have x go from 1 to 3. 1x 3. Right? So our integral, I'm just going to call this I. Right? So I equals, I'm just integrating x 1 to 3. And then we put x dx. I got x dx plus y, 2x minus 2, dy, which is 2 dx, divided by x squared plus 2x minus 2 squared, 1/2. And I got a whole thing that's just a function of x. Okay, a little bit of work to do here in simplifying this. So that would be, so x dx, 4x, 5x, so that's 5x minus 4 dx. Okay, and then we got on the bottom here, we got the square root of, all right, fine, x squared plus 4x squared minus 8x plus 4, right? So this thing equals 3, 1. The top is as simple as we need it to be. The bottom becomes 5x squared minus 8x plus 4. Okay, that's what we've got. Okay. So I got something quadratic and something not quadratic. We're going to let u equal 5x squared minus 8x plus 4. So du dx would be 10x minus 8. Right? So that means, and no, this is really interesting. So that is 2 times 5x minus 4. And that is the numerator. Okay. So this whole thing, if I go back up to the top here, right? This whole thing here, I equals x equals 1 to 3, and then I've got d2 dx, so that's 1 over 2 du square root u. Okay, looks good. So that becomes 1 over 2 u to the 1 over 2 divided by 1 over 2 x equals 1 to 3. I keep writing x equals 1, so I remember it's not u. The 1/2 cancel off, so this becomes square root of u, and the square root of u is right there. Right, to omit square root 5x squared minus 8x plus 4 at 1 and 3. Okay. So, square root, blah, 9 times 4, so 45, so 5 times 9, minus 24, plus 4, minus square root 5 minus 8 plus 4. So this becomes, so this is minus 20, so 25, square root 25, and then I've got minus square root 1, so this is 5 minus 1 equals 4, which is the same answer we got when we did the potential function. Okay, so that's it. That's the entire problem. Lots to these problems, right? They're kind of longish, but the good part is you kind of know. Now, if we got 6 here, or minus 2 or whatever it was, remember, it doesn't mean this was wrong. It could have been the potential function was wrong, but one of the two, at least one of the two is wrong. They could both be wrong, right? But you know that those things are supposed to add up to each other. So in this kind of problem, it was do this field, show its path independence. We showed it's conservative. Once it's conservative, we know there's a potential. We find the potential, endpoint difference, calculate the answer. We also know we could use any path between the 2 points. And you could use different paths. You could go here, then here, and have the sum of those two integrals. It would give you the same answer, or it needs to give you the same answer. Right? You go through here. Was any one of these easier than the other? Probably not really. The potential function took about a board. The path integration took about a board. Showing the thing was conservative in the first place took about a board. It's all pretty balanced in this particular problem. Okay, but that's the example of the utilizing conservative fields in the context of a line integration and the solution to this particular problem on the midterm for 2025.